Good. Okay, let's have a hand for Jason.
Cool. Hi, everybody. Everybody sober and ready to learn? I have stickers at the end, by the way. Please help me get rid of them. In the JavaScript landscape, you have to buy the amount of stickers that your project will live for. So it's really important that you go through them fast. Okay, and by the way, there's nothing actually loading there. It was just part of the talk. Okay, cool. So my name is Jason Miller. I live about an hour west of here. West? So Hamilton. Kind of up in the woods. I am develop it on GitHub and _develop it on Twitter. I will pay anyone $1,500 if they can get me my real handle there. It's been 4 years of asking for that. But yeah, so I'm a serial library author, which is kind of why I'm here today. And the reason why is because I get obsessed with constraints. I've been building mobile web apps since the dawn of the mobile web as we all actually care about it today. So iOS 1, Windows Mobile 5, back when the mobile web had scroll bars. I built a lot of UI frameworks along the way. And one of the reasons is I find constraints to be very interesting challenges. And because I have something called ADHD, which probably a lot of you are familiar with, I work best when I can sink my teeth into a given challenge and just kind of gnaw on it until I'm sounding like a beaver here, but gnaw on it until I've wrapped my head around it and I've solved the problem to the best of my abilities. So for the past couple of years, the constraint that I've been obsessing over has been file size. It's something that I think we are only just starting to appreciate on the web. For a long time, when the web was the desktop web, it didn't matter so much. We had huge computers, we had huge websites, and it was fine. But now we're not really in that era anymore. Most computing happens on a phone where we have these insane constraints we have to deal with. So I like to think of this as like a quintessential optimization problem, right? The same as any other. We want to maximize our productivity as developers, but simultaneously we want to minimize the effect of that maximization on the size of our code. And I know that's a lot of words. Basically, we want to sit on the shoulders of giants, but then compile those shoulders out. I was trying to come up with a graphic for this. It doesn't exist. And I'm a terrible artist, so as you can tell. So I'm here today to talk about Preact, and just super selfish show of hands. How many people here have heard of Preact? Cool, so 6 people. That's awesome. Okay, so that's cool. I'm going to explain a lot more about how Preact works than what Preact is. You'll get a sense of it, but I'm going to try and get into some of the nitty-gritty because what I want to do is kind of unscare a lot of the things that Preact does so that anybody here would be capable of writing a Preact and would feel comfortable doing that. So if you're new to Preact, you're probably wondering, what on earth is this? Why does it have a name that's almost exactly the same and logo that's almost exactly the same as React? This is Preact. It's harder to see in this light, but you could probably read most of this from where you're sitting, unless you're in the back. So it seems simple, right? This is the entire code base on one slide, but we're actually going to spend about 45 minutes dissecting this code base. In particular, these 2 sections, those are very important and very poorly understood. I have no idea why. But then also the section that I've highlighted here, don't worry, this is more of a joke. Really, what is he talking about? So, we want to cover the section here, and then we need purple because it's a Preact presentation. I have no idea what that's highlighting. It probably doesn't matter. But none of this actually matters until we've gotten through some of the core concepts, the first of which is JSX, right? Putting our HTML in our JavaScript, the unholy mashup. If you're not familiar with JSX, don't worry, it's very easy to understand. It's easier to understand than it is to explain, so I'm going to rough through that with you all. By the end of this talk, you will all have gotten out your laptops, rewritten your Webpack configurations in JSX, and then written them back in JavaScript after realizing how terrible of an idea that was. And if you don't believe me, here's the Webpack docs telling you how to write JSX for your Webpack config. I have no idea why they added this. It was a joke tweet I did. You can see there's a Preact cameo in there. Actually, the whole Webpack docs are even rendered in Preact. A lot of people don't realize that. So it's kind of like a weird full circle thing to be in this presentation. So what is JSX though? Why would we write our Webpack configuration this? Don't do that. JSX is an XML expression that's not part of JavaScript, the language, but compiles to JavaScript, the language. It just compiles to JavaScript function calls. It really doesn't have any other integration with the language whatsoever. So it's a specification that defines an extension that will never be merged into the language, which is great. It's kind of a standalone thing, but I mean, it's sort of great. But the idea is we write this stuff on the left, and then we transform it to the stuff on the right before we ever run our code. So there's no interpreting that has to happen here at runtime. And to me, the whole point of all of this is that it would be totally fine for us to write the thing on the right by hand. You wouldn't quit your job if your architect or whoever told you, we're going to write H functions. You'd probably wonder why they were your architect. But there are lots of people who do this. Like there are people who use Preact by writing the thing on the right there. And to me, that's kind of the value here. Is you don't need to necessarily understand JSX to understand React. You don't need to understand React to understand JSX. They're completely independent. So what is JSX at its core? Basically, it's we take the stuff on the left and compile it to the stuff on the right. And there's two key things that we've added into this that's adding slight complexity here. The first is if we have curly braces in our JSX, we're going back into JavaScript land, right? Similar to how you could have an escape hatch in a template language. This one's a little bit more literal. It's just an expression. You can see on the left there we have one and world. I hope you can see that. And then on the right, it gets transpiled to one and world. So they're unaffected. The curly braces are what do that. And then the second thing is on the left, we have link. And the uppercase, the first letter of link is uppercase in the tag name there. I don't know if that's visible. It may not be. But so if you have a JSX element with a tag name that begins with an uppercase character, that is going to turn into a variable reference in the resulting code. And you might be thinking, this is cool, but the thing on the right needs a spec. It sort of has that. So the thing on the right is essentially a function call that's going to adhere to this signature. This never changes. So this is the other half of the JSX spec. It compiles your stuff to an H function, or create you can actually define what the function name is, but an H function with no name attributes, and then the rest of the arguments are going to be called children. This is the only implication of that expression. You get to define what H is, which is horrendously important because this means that JSX is not associated with anything that uses JSX. And if you're thinking to yourself, that's great, but give it a name, the name is sort of hyperscript. Hyperscript predates JSX by many, many moons, and it's almost the same. So in this first example here, you can see obviously the left and the right are pretty much exactly the same. But in the second example, hyperscript has this extended syntax where you can specify like CSS selectors in the name, and it will auto-parse those and create attributes that correspond to them. I personally always thought this was a little bit weird because the whole point of hyperscript to me was that you get to skip an HTML parse. You can write your user interface in functions. But this is a parser, and it's like a quarter to a third of the hyperscript code base is dealing with these strings. So I'm kind of happy that JSX doesn't have that. It does have the variable reference thing on the right that you may or may not be able to see. So we gain back a little bit of simplicity by dumping that one effect, and that's good. So if you're wondering, like, how does this actually work, I would recommend that you pull up the Babel REPL. This is a great way to kind of play around with JSX, see how it works, see what's an error, see what's not an error, see what kinds of literals you can use in that syntax. And it'll just live update on the right. You can't go back from these H functions to JSX. It's not so statically analyzable, but you can go from JSX to H. You can see we've got foo transforms to H foo bar with the attributes. Kind of plays out exactly how you'd think. The one thing that's worth noting in here is if you put an H inside of an H, passing H to itself, you get nesting. And that ends up being kind of important. What I wanted to stress here was that H and JSX, or create element in JSX, are independent of the DOM. They're independent of React. You can use these, for example, to make a Webpack config if you have no soul. You can use them to produce XML strings, and you might think, who's still using XML? I'm still using XML. I have to deal with the SOAP API, and generating SOAP calls using a DOM document is kind of a pain. Generating SOAP calls with JSX is super easy. It actually feels like maybe as good as JSON, and also you get type checking, so like kind of awesome. And you don't have to deal with whitespace because there's no parsers, there's no stringifiers. It's just functions that return strings. So it works really well, and it's not just for React. It's not just for Preact or the DOM. So that's worth noting. So now that we have JSX out of the way, we're going to move on to Virtual DOM. That's kind of the next stop on the journey here. So like JSX, Virtual DOM is a relatively simple primitive, but it's useful kind of independent of all the other pieces of this puzzle. So Virtual DOM is objects that represent a tree structure. Full stop. That's all Virtual DOM is. There's a lot of like fluff that gets added into this, but it's literally just objects that represent a tree. I like to think of it in my naive brain as a configuration object for how a theoretical DOM builder would create a DOM structure. So like you might have like a factory function that returns some whatever, and you pass it a giant options object. Virtual DOM is your giant options object, heavily nested and all that. So how do we get from JSX to VDOM? Right, we know how to get from JSX to hyperscript. That's a Babel transform or Buble or whatever other thing. Yeah. Someone's going to create one called Michael at some point, and it'll compile to Buble. Who knows? So the key is we saw that it compiled to H function calls. When we run those H function calls, we get to define that behavior. So all we need to do is define an H function that produces these configuration objects that we call VDOM. So we want to invoke H and get back virtual DOM. Broken that down, we want to write the angle brackets. Hey, we can see div. We want to write the angle brackets with the pretty syntax. We want to use Babel, Buble, whoever, to compile that to H function calls. And then we want to run our H function calls in a JavaScript interpreter and produce objects that look like this. This is sort of the quintessential example I'm going to keep rolling with throughout this presentation. So how do we do this? What is the function H that does this? I am disappointed to tell you this is the function H that does that. There's almost nothing going on. It kind of seems like you could use a JavaScript primitive to do this. I kind of wish you could, it'd be cool. So literally you pass it 3 things and it gives you back 3 things with the same names. It does collapse children. So lovely. So you might hear the object that it returns referred to as vnode. It's kind of a loose term. It gets thrown around. This is just a plain JavaScript object. It doesn't actually have a constructor. It doesn't have a name, but we call them vnodes just to give it a term. A couple other things here. You might want to normalize children. So if children is like an array containing a infinitely nested array with the number 1 in it, technically you would want to render 1, so you should probably collapse the nested array, just to make your life easier. You probably also want to pluck out null values and this kind of stuff, but in reality, you could write a virtual DOM library using this as your JSX factory, this probably 40-byte function. So this takes us from hyperscript to virtual DOM, having come from JSX to hyperscript. But all of this is only useful if you can then take that virtual DOM structure, that nested object we saw, and render it out to the real DOM, right, to create something useful, so it's not just a data format. So rendering JSX/hyperscript is actually a relatively straightforward process. There's really only 4 steps, and they all fit on this slide. So keep in mind the object we've got in the upper right there with the scroll bar. We're going to grab the node name value from that, in this case div, and create a div. Simple. We've all done this. We're going to loop over the attributes object, using object to avoid looping over undefined, just to fit it on the slide. And then we are going to call set attribute with the key and the value. Simple. We're just mapping something into the DOM. And then we're going to loop over the children, and we're going to set up recursion because we're going to take the virtual DOM element. In this case, our first child will be the string hello. Our second child will be this object with node name bar that you may or may not be able to see. We're going to pass that to render to realize just that node, and then we're going to append that into the node we're working on right now. So that's it. We take recursion and we set up nesting. The last thing we need to cover here is, you may have noticed that there was a string hello as one of the children there. That is not a node, and there isn't a DOM node called string that we can render. There is a DOM text API that we can use though. So if we encounter a string like hello exclamation mark, we just bail out early with the text node. Simple as that. So this is a virtual DOM renderer, but there's one key difference between this and how virtual DOM tends to work in the real world. And that is that I've called everything attributes to this point because I have a vendetta. But also because I got this wrong for about 1.5 years and was corrected. So I used to call it attributes. I used to map it to attributes, and I was in my own happy little world. And then I realized that there's other things in the DOM that you should be able to set, called properties. They're really important. And you kind of need both. So you can't use the first one because it's attributes only. You can't use the second one because it's properties only. You need both. And the interesting thing is Preact at 3 kilobytes can't have maps or whitelists. It really can't have any behavior of its own. All it can do is render things the DOM can already render. There's no room for anything else. Like it can't even have whitelists of event types. So it has to check. And the way that it does that is by inspecting the node. That is an in word, by the way. I realize it's invisible. So it says, okay, you want to set the ID attribute or property or whatever. I'm going to say if ID is in this div you gave me, then I know that it supports the property ID and I can set it via a property rather than attribute. If it doesn't, it just falls back to set attribute. Fairly simple. And so that's how it gets around having to have a whitelist, right? So this is actually really interesting implications. If you are defining custom elements, typically a custom element is uninitialized when you first render it. It has behavior that gets attached later on. And in that state, it's actually best to set attributes so the custom element can pick them up later when it self-initializes. And interestingly, when elements self-initialize, the overwhelming majority of elements will attach getter-setter pairs to each DOM reflected property on an element, which means further diffs of that will start to use the properties, which is cheaper. Even though custom elements or Polymer or whatever and Preact don't know or care about each other, they kind of interoperate nicely because they're both using these primitives exactly the same way. So you're probably sitting there wondering, hey, does this work? You're shouting a lot of words at us. Does it actually work? So here's an example. I should improve my screen. Here's an example. So you have a virtual DOM tree that is our fancy syntax. You pass that tree, which is at that point objects having been run to render, which we know realizes the tree to an actual DOM tree. And then you just append that into the body element. We can see on the right, it does exactly what we wanted it to do. Probably not well, but it does what we want it to do. So it works, put it on production. Just be happy you don't work with me. So we built a simple virtual DOM renderer. We built a terrible virtual DOM renderer because anytime data changes, it needs to rebuild everything from the root. And if you have used React or any of these other libraries, you realize that that would be a really, really, really poor way to do this. You wouldn't be able to compose views, which seems fairly important. So anytime data changes, got to do a re-render. The diff algorithms that power virtual DOM libraries are kind of what make them viable. They're not required in order for them to work. You could build a really slow VDOM app this way, but you would never want to put that in the hands of the user. So one unfortunate thing is these kind of are enshrouded in mystery, and I'd like to demystify some of that for you guys. So the principle behind virtual DOM diffing is, what if instead of rendering top-down, create diff, create diff, create diff, all the way down, we actually looked at the current DOM structure. We looked at document.body.child nodes and figured out whether it sort of matched what we were diffing. And we iterated down the tree, kind of taking into account the fact that there may already be nodes there that we want to mutate rather than destroy and recreate. And that's kind of the fundamental premise of how all this stuff works. If you look at the DOM's API, which is the thing on the right here, and the virtual DOM nodes we just created for ourselves through H, they're almost exactly the same. The names are uncannily similar. One notable exception is children and child nodes. There is a DOM property called children. It just doesn't include text, so it's kind of useless to us because text is important. Maybe the most important thing that VDOM libraries render, as we'll find out later. But you can see how you could just kind of loop over the stuff on the left with a for loop or whatever and compare it to the stuff on the right. Fairly straightforward. And virtual DOM diffing isn't really that different than that. I wish I could say it was cooler. It's not. It's 3 steps. The first is we look at the type of the element. And then the second is we look at the children. And the third is we look at the props or attributes that are things that are going to end up as properties in the DOM. We didn't give them a real name. So the first step, we jump into, if you loop over children, then that's how you set up recursion. Important. So the first step is to diff type. So the easy path here is if a node is not owned by a component, we're going to look at the type of the virtual DOM node. In our case, it would be a div. and the type of the real DOM node. And if they don't match, we're just going to throw out the real one and make a new one. It's not useful to us. You can't change the type of an element after it's created. It's immutable. If they do match, though, we could just keep diffing down the tree. We don't have to do anything. So that's nice. If the element is owned by a component, slightly more complex, we need to create a backing instance of that component to match the constructor. And the constructor is just hanging off of the element as a property. And then render it out. Rendering that component gives us more VDOM to apply to the DOM. So it's just a cycle. Comes back to the beginning nice and easy. Second step is children. So first thing we got to do is we loop over all the children in the DOM, collect them up into two groups. One is unkeyed. And these are stored in an array because they have order. And the second is keyed, which are stored in an object map because they have keys, right? So rather than being a linear sequence of DOM elements, they are just named. The second step is we loop over our virtual children in that JavaScript object, and we find their matches in the lists we just created. Importantly, when we loop over the unkeyed list of divs and spans and whatnot, we want to find the first instance of an element of that type. So we want to find the first div in the list. And we pull it out so that we don't reuse it in the next iteration. Then we take that match, or null. It's okay if it didn't exist. We just created a new. We take that match and we pass it back into that diff function we just wrote in the previous slide. And then whatever DOM node that gets back from that, we just insert it at that index in the DOM, the index that we're at in this loop over the virtual children. And the third step's really easy. If there's anything left, destroy it. Okay, so I mentioned keys before and glossed over them. This is horrendously important and also horrendously misused. So if you could take one thing with you, please understand keys. So keys attribute meaningful order to a uniform set of elements. They do nothing more than this. They are useful because by default, a virtual DOM algorithm is going to add and remove elements at the end of a list. It will never do anything else. It diffs top down, and in the DOM, top is, first child. So what does this mean? Let's give ourselves an example. We have three elements. Those are LI elements, by the way. I will just describe. So we have three elements in our first render, 1, 2, and 3. And then we have a second render here with the elements 1 and 3. And you and I looking at this can see, oh, yeah, 2's gone. They removed 2. But we didn't tell the virtual DOM renderer that we removed 2. We just gave it 2 elements that happen to have some text in them, and it doesn't know that 1 and 3 aren't consecutive. So what it's going to do is it's actually going to run through, see the first one's the same, and then it's going to see that the second one has new text in it called 3. And it's going to update the text of the element, which seems stupid already, but we'll give it the benefit of the doubt. And then it's going to get to the third element and say, oh, there's only 2, and it will delete it, which is 2 DOM operations when there was very clearly only 1 that was supposed to happen, because our DOM renderer it's fully generic, it's dumb, it doesn't know about this data. So in a keyed scenario, though, if we pass 1, 2, and 3 as keys in our first render, and 1 and 3 as keys in the second render, 2 is missing in the second render. That's data that the DOM renderer can use. So it's going to run through, it's going to be like, okay, yeah, 1's the same, no difference. It's going to hit the second one and be like, oh, the key's wrong, remove, done. I don't do, if something is not in the second diff, I delete it. And then it gets to the third element, and it sees, I already have an element with the text 3. It's at position 2, which is the new offset because we deleted an item. I don't have to do any work at all. So it deletes one item instead of setting the text and deleting the second item. So that's the entirety of how keys work. People like to add keys to elements. There's not a huge cost to adding keys unnecessarily, but there is a cost. And it's something to keep in mind. And sometimes it can have very weird side effects. CSS reflow is more expensive when you use keys in a list in many situations. So keep this in the back of your mind if you're writing React or Preact code. And then the last thing is super easy. So attributes, props, whatever you want to call them. We loop over the ones that are in the DOM, and if they're not in the virtual DOM, we delete them. Simple. We loop over the ones that are in the virtual DOM, and we either add or update them in the DOM. It's the same operation, so we get off free there. So we've built a virtual DOM renderer at this point. It's done, and there is no more problems on Earth. When in reality, what we've actually done is we've built a library that encapsulates all of our problems into one place, maintained by a small group of people, which is dangerous. So what I'd like to talk about is a little bit of the performance things that I've learned in building this application. So the first is that people say the DOM is slow. This is, I'm not going to combat this. This is true. The DOM is slower than Canvas or any other immediate mode drawing API. That's fine because that's not an apples to apples comparison. That's like an apples to guava or whatever it's called comparison. Pick a fruit. Because the DOM gives us a boatload of stuff for free. It gives us accessibility for free, right? Annotate your stuff with ARIA attributes and titles and all good properties that we know, write semantic markup, and your site will be accessible. There's some specs to read, but it's there for you. It's extensible by default. So like when I install an extension to add emoji input to Twitter, it doesn't know about Twitter, and Twitter doesn't know about it. They just both know about the DOM. It's the substrate that both of these things are built on. And in the same vein, it's framework agnostic. So I can write an app in Preact that renders web components, and they don't know or care about each other because they both just use the DOM. So the speed of the DOM is kind of subjective depending on how you look at it and what you're getting out of it. It's also very dependent on how you use it. So here's a few tips on how to use it. Let's get right over that. So first one, sounds stupid, but surprisingly often misused. If you were using text in the DOM, use text nodes in the DOM. Almost no one does this. It's really confusing. So just use text nodes in the DOM. The API is really straightforward. It's almost exactly the same as the element API, but it's just a lot cheaper. So this is the text API. You can create a text node with some text. You can insert it into the DOM at a given position, and then you can change the text. Missy Elliott joke, I think. But so it's easy to see why this is faster because it does less. There's no parse. That was late. So there's no parse here. So we're not setting inner HTML and firing up the browser parser to set some text into an element. We're not setting text content, which does a lot of extra work. We're literally just creating some text and inserting it into a node. There's no parse. Text content does a lot of stuff. It will remove HTML elements that were there before. It will normalize adjacent pieces of text into one piece of text. And none of that stuff is free. In fact, the overhead for a typical application of this, in terms of my own benchmarking, is around 50%, right? So these are things that if you're pierced down through the primitive you're using, or if you are writing raw DOM stuff, you need to be cognizant of. It also kind of floats up even if you are using something like React or Preact, because if you mutate the DOM and keep recreating an element, but really are just trying to set its text content. So if you have like a key on a div that always change, or you're switching between a div and a span, that's horrendously expensive as compared to just changing the text content of a node. This comes into play with stuff like localization, rendering text in spans. One span with a lot of text is a lot cheaper than many spans with small amounts of text. So just try and use the one that matches up to your use case. The third thing is don't use DOM getters. They suck. They're terrible and they're not a good idea. They're required, so I'm not bashing the DOM here. It's the only way to get certain things done, but they can't be optimized the same way property access can. And here's an example of inspecting that to see. So every node in the DOM has a node type property. It's an integer indicating, what the type is. In the case of a text node, it's 3. So you would think that the text.prototype would have a node type value of 3. It doesn't. It inherits from node, which is a getter for node type that checks the type of the element and returns an integer corresponding to whichever one you called it on based on context. And that is horrendously expensive. So code that looks like it would be fast, like this top thing here, an integer equality check should be fast. Not fast. Really slow. Code that looks kind of stupid, like checking for the existence of a split text function, very fast. And then something I'm going to touch on in a second, doing an explicit check to see if something is defined or undefined is far and away faster than even the second example there. And just to prove that I'm not making all this stuff up, here's a benchmark. And so Preact does this probably 1,000,000 times over the life cycle of a given app because it's constantly re-rendering and checking to see if something is text or not text. And obviously, the clear winners here are split text and remove attribute. Remove attribute's not useful for reasons I'm not going to get into, but split text is important. We have getters. Constructors are just don't go there with the DOM. They don't work well. But these properties are really cheap to check. And then the last one is never use live node lists. We are all guilty of this. If you have used children or child nodes, you are guilty of this. And it's okay. There are cases where it's just the easiest thing, and it makes sense to use them, but just keep in mind that they're really slow. And there's no way for the JavaScript engine to kind of save you here. As an example, let's say we wanted to remove all the children from a parent element. The first one is what you'd probably write if you just had to do this task, get it done, out the door. Loop over the children backwards, oh, we're going to save an allocation or whatever, trying to be good about performance. But the problem is every time you iterate, you're diving into an object that is like this crazy proxy into the DOM. And it's not an array. It's about the furthest thing from an array. It just has the same API. The second example, though, is really cheap. You're just checking if a property exists, storing the value to avoid a check and then an allocation, and then removing it. And eventually, parent.lastChild will be null, and the loop will exit. So like a property access in JavaScript is super cheap. This one is a DOM getter, so I'm already contradicting myself. But it's a DOM getter that is way cheaper than a whole bunch of crazy DOM interactions from the first example. And so here's a performance test. Just the thing to keep in mind here is there's a ton of overhead in setting up the elements to then tear them down here. But it's consistently much faster to use this last child technique than the child nodes technique. And I know what you're saying. You're saying, Jason, I don't do my own DOM manipulation. I have people for that. I don't. Tell me about your people. So my point to you is just always profile. Always know how your code is running in situ. Easiest way to do this is Chrome DevTools. You've all seen Chrome DevTools. Probably some of you live in Chrome DevTools all day like I do. There's lots of information there, but one that I wanted to point out was just the width of the flame. I'm not smart, so I like little metrics that I can track that are just like pixels on my screen that I can measure with my eyeballs. You should see me build stuff out of wood. It's really sad. But basically, this gives me like a little metric, like if I'm rendering my application, as fast as I possibly can, how long does each render take? Can I see that on my screen? So like if I make an optimization, does it go from 6 to 3 roughly on average? Easy. And when you're super zoomed out, you can kind of just judge by the width of the bars. This is like super coarse, but it works really well as like an initial metric. Second one is IR Hydra. This is like super deep. So if you're doing really performance sensitive code, like maybe you're writing, data massaging that needs to run really quickly, you may want to dive into this. Basically, you're going to run Chrome or Chromium with some flags, produce debugging output, and then you dump that debugging output into this web-based tool written in Dart, interestingly. I think I'll get shot for that. I think it's written in Dart, but you pipe that into here. It doesn't upload or anything, it's just locally. And it will actually tell you based on not only the structure of your code, but the actual data flowing through it in your sample, what de-opted and what got optimized. And it will show you the intermediate representation of your code and the bytecode that it generated. The bytecode, for somebody like me is just completely unintelligible, but it'll point out like in little pretty purple, blobs. Oh, if I hit this section of your code, I'm going to kick you back into non-optimized mode, which is like a huge red flag. And it just gives you this little spot in your code where you're like, okay, what's dumb about this part of my code? What can I fix here? And it's kind of a nice feedback tool. It's a little bit hard to get set up, so there is a URL that should show up in a second. Yeah, there. Okay, so if you go to git.io/HydraOSX, I'm never going to give that up. That's how to run this on macOS. I don't know how to do it on Windows yet. It's just Chrome flags, though, so if you know how to run Chrome with flags, there's like 17 flags in there. Just put them all in. And then you could just take that and dump it into IR Hydra. You might find it really interesting on your code base, especially if you have like third-party code in there, just kind of looking at what it's doing underneath the hood. Second tool is ESBench, third tool actually. ESBench, this was unsurprisingly the first Preact app. Preact kind of comes from a place of performance, and I really, really wanted a graphical tool. JS Perf went down for about a year, and I was dying. So I wrote ESBench as quickly as I possibly could. It is still that first version from September 2015, so like I make no amends for the visual foibles. But it's really useful. It's basically just benchmark.js and Babel stuck together. It's like a 2 meg app, so I'm sorry, but it just runs your code through Babel, creates your benchmarks, and then it runs them and shows you a little graph. And this is really useful because you can just like have 5 different implementations of a function that you really care about and literally just see like, oh, this one is like terrible compared to this one. And as long as all the outputs are the same, go with the fast one, nice and easy. The only thing to be careful of with this and with any other micro benchmark or benchmark in general is it's exceedingly easy to test nothing in JavaScript. It's the easiest thing to test actually. If you write a function that has deterministic output, it will probably get optimized away and run very fast. Heavy air quotes. If you write a function and you pass it similar data, like people would declare like a test object, just keep passing the same object, it's the optimizing compiler in JavaScript is going to kick in and essentially inline only that code path for that object and nothing else. So you're testing something that is as far from real world usage as you could possibly test. Right, realistically, what you want to do is you want to test your function monomorphically and polymorphically, and worst case, megamorphically, depending on how many types you're going to pass it at runtime. And it just depends on, so the only thing I can recommend, and this is really easy to follow, is use real data, just grab a sample from somewhere, and try and use the output of a function you're testing. Like if I'm testing that H function, I'm going to write a little shoddy little virtual DOM renderer that like takes it and does something with it. And that way I know that I'm not making false claims about H. So some lessons from this. The first is be explicit. Don't accidentally cast. We saw this a second ago, but I want to clarify. So if what you want to know is that something exists, don't ask the JavaScript engine that it exists and is not 0, not an empty string, not null, not undefined, etc., etc., etc. You could use has-own property in certain situations, but it doesn't account for prototypes. I would recommend just checking to see if something is not equal to undefined. People on the V8 team are trying to popularize this. I'm going around trying to popularize this. It doesn't really add any weight to your code. I think it's about 5 bytes overall for Preact to switch to these checks from the first ones, and it's a huge performance gain. If you're ever in doubt, if you tell the JavaScript engine more, it can optimize better, plain and simple. So this is one case where that's true. Second is inline helpers. We all like to write functions to do work for us. They're like little robots, and that's great. But if you write super generic functions and pass them all manner of data, they are never going to get optimized. Or they're going to get optimized, and then you're going to pass them a bunch of new stuff, and it's just going to train wreck. This function used to be in Preact, exactly as written, and somebody submitted a pull request to take it out, and it improved rendering times by 10% overall. One-line function. And this is crazy because most of Preact's rendering time is governed by DOM interactions, and this has nothing to do with the DOM. It was just JS runtime. We just converted them to raw function calls. A little bit of overhead, but when you understand gzip and how it dedupes, duplicate things in your file, it's really not that much. And then the last one is really it's silly, but take this to heart. Short circuit. If you can bail out, bail out. I'm not necessarily talking about early returns. It's not quite that simple in JavaScript, but if you can prevent calling a function, prevent it. If you can prevent diving into a recursive algorithm, do that, because recursion is expensive. We don't have tail call optimization. But this quote is from me, by the way. That is super facetious. So here's an example from Preact. So Preact, if you have one text node in the DOM and one text node in the virtual DOM, and we're like halfway through the tree, it's going to see, oh, there's nothing I can diff for text but the fact that it's text. So I'm just going to blast out that text update to the DOM and then be done with it. It just exits the algorithm early. This is the single largest optimization that has ever gone into Preact. It's a little bit of extra code, so there's some weight there, and it seems weird. It's like adding a bunch of if statements and checks even into DOM properties that are expensive, but there's so many text nodes in typical application that it's way offset by the performance gain. So that's a lesson learned there. So all of these things are to kind of say, we should try to make decisions based on data, like a scientist would. We should try and collect better data. We should try and write better benchmarks and more benchmarks. We should write performance tests, especially if you run them in CI. And then act on that by setting more informed goals. We all have a shared goal of creating faster and better web. And that's how we're going to provide better experiences to people who are frustrated with this. Thanks.